Hey guys, welcome. Yeah, so basic practice video with 4 examples after a brief discussion, and I'll have videos on harder practice and possibly very difficult practice with their own set of examples. Yeah? Okay, cool. Now, I'm going to assume that you have a superficial understanding of antiderivatives, and so then, we should start with this. Let's start by writing d dx sine x. If I write this, right, you're going to say that this should equal cosine x, and that's because you know that the d dx is telling you take the derivative. Take the derivative of what? Of whatever I've written after me, so after d dx, right? And that's d dx speaking in first person. So yeah, take the derivative of whatever written after me, and that's sine x. So the derivative of sine x is cos x, and so we do this. So then let's think of taking derivatives, so d dxing as a forward movement. Then antiderivatives, which I guess we can call sigmaing, because antiderivatives come with the instruction given by sigma, whereas derivatives come with the instruction given by d dx. So just as d dx means take the derivative of, this means take the antiderivative of whatever is written after it. And so let's write cos x, and just like sigma, ever present with antiderivatives is a dx at the end. So in future videos I'll explain. I'm sure there are videos out on why you have to write this dx. So you could, if you're very eager, learn before I make my video on it. But anyway, this here means find the antiderivative of cosine x. So it's saying, what is cosine x the derivative of? That's basically what this whole instruction is saying. What is cosine x the derivative of? We know that cosine x is the derivative of sine x. So then we see that the antiderivative of cosine x is sine x. Now, I'm going to say that here, technically I could have written sine x plus c, because what is the derivative of sine x plus c? So if I did d dx of sine x plus c, well, the derivative of sine is cosine, so I'd write cosine, but the derivative of the constant c is nothing. So you see, because sine x plus c has derivative cosine x, technically my answer to the antiderivative of cosine x dx, well, or cosine x dx antiderivative. So basically when I see that, my answer should be sine x plus c, because it's possible that the antiderivative had a plus c that was lost in the differentiation, in the forward movement. So the complete answer is not just sine x, but sine x plus some unknown constant c, yeah? Okay, so that's what we should say is the antiderivative of cosine x. All right, cool. So you're getting the hang of this, hopefully. So you see, one way to find antiderivatives is just to recognize, what the function inside of sigma is the derivative of. So if you know that this is a derivative of something you recognize, then great, you're done with your antiderivative. But as you'll see, like if you continue on to study Calc 2, methods for finding antiderivatives can get pretty sophisticated. So they're not always easy to find or just easy to recognize. I promise you that because this is like your first lesson, that all of these examples, even the ones that appear difficult, will be made simple. Yeah? Okay, cool. So what else should I tell you? Well, I shall also tell you that... Wait, why aren't you erasing? That's my instruction. My instruction is delete. Why aren't you following instruction? I don't know. Like, I did it twice prior. Anyway, okay. Cool. So before I start, anti-differentiation or antiderivatives, by the way, antiderivatives are also called indefinite integrals. Indefinite integrals. So if you see in some books indefinite integrals, they're saying antiderivatives. Yeah, so indefinite integrals or antiderivatives come with a few properties, like, and one of the properties is the constant rule. So if I have, like, let's call the constant a, if I have the antiderivative of a times some function f of x dx, then it's as good as finding the antiderivative of f of x first and then multiplying the result by a. Yeah? Okay, cool. That's one thing that's true about antiderivatives, but we need a couple more properties in order for us to go through the example successfully. So what are these other properties? Another one is this. Another one is like the sum and difference rule, which is that like if we have the antiderivative of like f of x plus or minus, doesn't matter if plus or minus, either of the two, plus or minus, g of x dx, then this is going to be equal to the antiderivative of f of x dx, and then plus or minus whichever came with over here, yeah, like, yeah, correspondingly, yeah, and then the antiderivative of g of x dx. Okay, now, by the way, whether or not we are casual in writing dx in this manner, or we put the effort to put parentheses around what's written before it, dx is actually multiplying everything before it, whether or not we put these extra parentheses that I put on in white. In fact, frequently in books, like, because it's understood that you know that it means like the same as putting the parentheses on, and that is you understand that dx is multiplying everything in front of it and written after sigma. Like, you know, it's we don't take the time to write these parentheses in white that I've put here. But yeah, that's why, like, you know, we have a dx here and there. Like, it makes sense. Yeah. Okay, cool. All right, so in addition to these two properties, we need one more, and then we'll be you know, on our way to working on the practice problems. Yeah. Okay, cool. All right, so what is that one more? Let's see. Let me reduce this to a manageable size. So I guess we could also number them. So this is property 1 and this is property 2. And now let's write property 3. Let's leave it space, but on the discussion, let's do over here. Now look here. So if I wrote ddx, right? If I wrote ddx, and then this is going to feel a bit inventive why I wrote this, but ddx of x, you'll see why I wanted to write this, x to the n plus 1 over n plus 1, right? N plus 1, right? And of course I could, if I want, have a plus a constant, but I'm going to leave out the plus a constant. You saw the deal with plus c, right? Like, it gets lost in differentiation if you have a constant added to anything, right? Okay, you only need to worry about the derivative of that other thing, not the constant. You know that. So what is this? It's going to be, well, n plus 1 times x to the n plus 1 minus 1, and then of course I have the n plus 1 in the denominator, and of course this n plus 1 is just one number. It's the same number as here, so these guys cancel. N plus 1 minus 1 is x to the n. So we see that the derivative of x to the n plus 1 over n plus 1 is x to the n, and therefore the antiderivative of, and I should write this in green, so therefore the antiderivative of x to the n plus 1, or rather, sorry, the antiderivative of x to the n dx, because the derivative of this is x to the n, the antiderivative of x to the n dx should be this. As I said, sigma, the antiderivative symbol, is always accompanied by dx, so don't worry when I say like antiderivative of x to the n that I also say x to the n dx, and so I say the dx after. You could just, if you want, say the antiderivative of x to the n. But yeah, anyway, this here we know should be what? It should be x to the n plus 1 divided by n plus 1, and of course if I wanted a plus c, right? So all right, so we know that I need to write over n plus 1, right? Okay, n plus 1 and then plus c. I don't know if I'll dedicate a different video to explaining this further, which is showing that the antiderivative of x to the n dx, or the antiderivative of x to the n, is this. I don't know if I'll dedicate another video to this, but I think I explained it sufficiently, and you could experiment with like x to the 5th and whatever, right? Like, so yeah, but this should be pretty clear. And also we started our discussion saying like derivatives are forward movement, so if I take a derivative to go from here to here, then I should be able to use an antiderivative to go from here to here, right? Okay, so you can even think of it in the terms we talked about earlier, forward and backward movement. It makes perfect sense that the antiderivative of x to the n is x to the n plus 1 power divided by the number n plus 1, and of course possibly a plus c, right? Okay, cool. What did I do that for? I need to get rid of this because we need to start getting on the practice problems. All right, so we've got our third and final important property handy, and we're ready to do some practice. All right, practice? I'm not talking about practice, my favorite like basketball player ever, and that was taken out of context, in case you didn't know. Anyway, if you didn't know the reference, okay, too bad. So like with this guy, like, right, we first use the property 2, right? And using property 2, we could write it as cos x dx, and then plus, and then integral of 1 over x dx, right? Okay. And remember, I like forgot that you know how to quickly exchange between the word antiderivative and indefinite integral, and I used integral for short for indefinite integral, but yeah, antiderivatives are indefinite integrals, so I'm allowed to say the indefinite integral of 1 over x dx if I wanted. But yeah, so anyway, this is what we do using this property here, and lucky for us, we recognize both this guy and this guy, right? Like, so here, this is asking, with sigma and with cosine x and dx, this whole thing is asking, what is it that I took the derivative of to get this? Well, you must have taken the derivative of sine x to get to cos x. So the answer to this is sine x. And of course, you should know this from the discussion at the start of this video. And of course, I have a plus c, but I'm going to get a plus c from this integral, so some unknown constant from this integral. And then I'll also get some unknown constant from this integral. So I can lump them together into some unknown constant, because the sum of two unknown constants is just still an unknown constant. So I'm going to write the plus c at the end after I'm done with both of them. Now, this here we look at and say, what is it that we took the derivative of to get 1 over x? Oh, natural log of x. So ln of x. So plus c. So all we demonstrate in this first example is the fact that if you can recognize your antiderivative, then you're done quickly. And so this is like the most basic type, right? Like, because like, you know, like this is just a matter of like memorizing, and you might have to do more work than just memorizing, which will be the case in the other examples. Yeah. Okay. Cool. Now, so let's go on to this second example, which might have been better done as like a third example, but I don't know. It's okay. Like, I think they could be done in either order and still be fine. So, like I'm saying, we could go to the third one if you want, but I don't know how to get your input. So, let's go on with the second one. So using this sum and difference property, we could write sine x. Let me leave some space. You'll see why. Sine x dx, and then plus, and then integral of, and then it's x squared cube root of that, which is the same as to the 1/3 power, right? And then dx, right? Okay, cool. Now, if you look at this and ask, what is it that we took the derivative of to get sine x? There is nothing that comes to mind, like just off memory. But there is something that when you take the derivative of it, you get something very close to sine x. And that is taking the derivative of cos x, right? It gets us to the derivative of cos x is equal to negative sine x, right? And so if there was a negative sign right here, then we know or recognize this antiderivative. It's going to be cos x. But there isn't that negative sign right there. So how do we adjust? Well, how about this? Throw in a negative sign here. And to make up for putting this negative that wasn't there, we could put a negative in front. And then now we know that this here, the antiderivative of negative sine x dx is cos x. But because of this negative all the way out, the answer to the antiderivative of sine x dx is negative cos x, right? Okay, cool. And yes, you could write plus c, but let's wait on the plus c after we're done with this guy. But yeah, we're done with our first antiderivative. Well, after we've split the original problem into two, and the second guy is going to take a little bit more work, but it's okay. So plus we go, and then this is x to the, using exponent rules, we could write 2/3 power dx, right? Now, looking at this is of the form x to the n dx, right? Antiderivative of x to the n dx, right? And that's what we have here. Yes, n is a fraction, but n is allowed to be a fraction. You can still use this third property even if n is a fraction. So if we use that third property, then we know that the answer has to be, well, first we still have the answer from the antiderivative of this first guy, and so that's negative cos x plus. Now the answer to this, using this right hand side, will have to be x to the, well, we need to add 1 to n, so to the 2/3 plus 1, and so this is n plus 1, and we know that we have to divide by n plus 1, so we go this divided by what is 2/3 plus 1? It's 5/3, isn't it? So 5/3. And then, we had a plus c from here and plus c from here that we combine into just 1c. So plus c here. And the only thing left to do here now is to simplify this a little bit more. And I'll help with that because yeah, why not, right? Okay, so, all right. So how do we simplify? Well, there's only one thing to simplify, and it's in the middle part, right? And so that is we write negative cos x, and then we write plus. Dividing by 5/3 is the same as multiplying by 3/5, so we can write 3/5, and then we know that this says x to the 5/3 power, but x to the 5/3 power is the same as x to the 5th, and then cube rooted, right? So x to the 5th cube rooted. So there we are, and then plus c. Yeah, okay, cool. So this is it for the second example, and so let's move on to the third example. So the third example says this. It's antiderivative of, well, first we could do this, right? 3 and then x to the 5th dx, and then minus 2 times integral minus 2 times integral, and then it's x to the 4th dx, right? And then plus integral x cubed, and then plus, and I'm going to take exception and keep the constant 2 inside here, and you'll see why I wanted to do that. And plus, finally, I'm running out of space, but I think I know what to do about it. How about this? I live in New York City, so I'm always running out of space. So, and then integral of e, and then dx, yeah? Okay, cool. And notice here, it's not e to the x, the function. This is just e, so it's like a number. So I might as well have written a 7 here. It's like trying to be fancy and using a fancy constant. But this is just the integral of a constant times dx, yeah? Okay, now here in this first part, we have the 3, but otherwise, using this x to the n situation, property 3, we add 1 to 5 and we get 6, and so 6 is n plus 1, and so we divide by it, and so there we are. And then minus 2, and then business as usual, we add 1 to 4, so we get 5, and we divide by n plus 1, and n plus 1 is 5 in this case, so there that is. And then plus x to the 4th over 4, right? And there's no constant in front of this guy. And yes, I forgot a dx there, but yeah, I hope no one cried. And actually that's a little crowded. Oh, and I like my d. I like my d, how it looks. So let's slide that, and I save the d. And does that mean I save the day? Hopefully for one of you, okay, cramming and stuff. Yeah, so the antiderivative of 2x is x squared, right? Because you're asking what is this the derivative of? Well, x squared, and that's why I kept the 2 inside. Yeah, okay, cool. And then plus the antiderivative of a constant is the constant times x. So here, e times x, because the derivative of e times x is just e. So it makes sense that the antiderivative e is e times x. Not e to the x, e times x. Okay, and then of course, what did I forget? Yes, you got it, plus c. There you go. Okay, finalement, one more. Right? And what more? Well, the last one, you've been staring at it for a while. Okay, so last one is, maybe you weren't, I don't know. So 1 over root x, we could first write as 1 over x to the 1/2, because root x is x to the 1/2. and then we have dx, right? And then plus, right? And then integral, and then it's e to the x, and then dx, and then plus integral, and then it's secant squared x dx, right? Okay, got it. Now, this first guy, we want to write a little bit more, right? Like, so x to the 1/2 in the denominator could be put in the numerator as x to the negative 1/2, right? So that's what I'm going to do. So I'm going to write x to the negative 1/2 right here, right? Okay. Right? Okay. All right, now over here we use property 3, and so we take x and to this negative 1/2, which is n, we add 1. So negative 1/2 plus 1 is positive 1/2. And so this 1/2 is n plus 1, which is what we have to divide by, right? So we divide by n plus 1, which is 1/2. So there that is. We're done with this integral other than simplifying this a little bit more. And yeah, dividing by 1/2 is multiplying by 2. So let's at least do that part now. Okay, so, and then yes, there's a plus c, but we won't bother. And looking at this, we're asking, what did we take the derivative of to get e to the x? Well, e to the x, because, yeah, the derivative of e to the x is e to the x, so comes as no surprise that the antiderivative of e to the x is e to the x. Okay, plus, and then we look at this and say, what did we take the derivative of to get secant squared x? Well, secant squared x is the derivative of tan x, so yeah, the antiderivative of secant squared x is tan x, yeah? Okay, cool. And then, of course, plus c. And we're done. I hope you enjoyed this. And soon to come is harder practice on antiderivatives. Okay, all right, keep watching. Take care.